microphone. Yeah, we're still waiting for people to trickle in, but I think the coolest people are here, so we can get going. Yeah, very welcome to Frontiers of Natural Language Processing. I'm Herman Kamper. I'm a lecturer at E&E here in Stellenbosch. I mainly work in low-resource speech processing. My partner in crime is Sebastian Ruder. He's going to help me. And then we actually have a great panel as well, a bit later on. I'll talk through the structure now. And then I hope to encourage participation from all of you. So basically it's a team effort. Okay, so there's three things we want to get from this session. Cho actually gave an amazing overview of a lot of the core concepts that's used in NLP. And we hope to kind of extend that a little bit. So we'll start by giving an overview of like the recent history of NLP. And Sebastian will lead that discussion, giving you an idea of the major advances maybe over the last 10 or so years. Then the second goal of the session is we want you to kind of walk away here with a good idea of what are the big open problems in NLP. And that's where the panel will help a lot to answer those questions. And we actually did a very cool experiment to kind of try and figure out what the world leaders in NLP are thinking about and are working on. So that's the second goal. And then the third goal is that I hope that we will get a sense of some of the things that the local community are working on, and to kind of maybe through the discussions, and I really hope that there's some audience participation, get an idea of what people are working on on this continent, and then maybe to start to think about some cool collaborations. Yeah, okay, so the first part of this talk is a review of the recent history of NLP, and Sebastian will lead that. So Sebastian has, did I screw up the recording?
No,
okay.
It's all good, it's all good.
So I think most of you actually know Sebastian, but he's worked at Microsoft, he's been involved with things at IBM, Google Summer of Code. He's currently a research scientist at Alien, and also a PhD student in NLP based in Dublin. I think most of you probably know him from his blog and newsletter, which if you haven't seen this, you should really subscribe to that, because he gives this amazing overview of like recent news in NLP. So without anything else, I'll just give over to Sebastian to tell us a bit about the recent history of NLP.
Cool. Yeah, cool. So can everyone hear me here? Microphone, yeah. All right. Yeah, so it's my pleasure really to be here today and to kind of give you an overview within kind of around 45 minutes about really some of the major milestones over the last 10 or so years. And for that, we've essentially asked the experts, which we're going to mention later as well, really what are to you really the most important developments, and to try to distill them really down to the 8 or so highlights that we were able to identify. And so as you can see here, most of the developments are actually fairly recent, although there have been, as I'm going to point out, like a certain number of kind of early advances that really have set some of the tone for approaches that are being used these days. So without further ado, I'm going to start off here with the kind of the first point here, and so I'm sure. So actually, Joe in his talk, and I'm sure those of you who have seen the RNN practical have actually had already some exposure to that. So the first point, or the first actual like really successful application of something along the lines of deep learning to NLP has actually been in 2001 for applying neural networks to the task of language modeling. So for those of you who don't remember anymore, so language modeling is essentially really the task of given a language sequence, given a sentence, to predict the next word in that sequence. So it's a very simple task, essentially the simplest task you can possibly think of when you deal with natural language. And as you've heard, kind of the earliest approaches, really in this kind of line of this task, have really been using n-grams with different forms of smoothing to deal with anti-word sequences. And in 2001, because recurrent neural networks were still very hard to train, so the first application of kind of neural networks for this task was really kind of a classic feed-forward neural network. And as we've heard before, in a feed-forward neural network, you need to predefine or to fix the number of, or the input dimension. So kind of in the original application, as we can see here, basically the network is defined as taking as input kind of the n previous context words here. So the context for this very classic model is essentially fixed, and then these embeddings or the vectors that represent each of these words are then fed into a hidden layer with an activation function using the 10H here, and then we finally have a softmax activation function, which is used to predict which out of the kind of n words in the vocabulary is used for the final prediction. And this model, like even if you don't, it was proposed in 2001, and besides kind of now current models using more recurrent architectures, this essential architecture has pretty much not undergone many changes actually over the last 15 years or so. And this initial lookup layer, where we have a vector representing each word, now is commonly known as word embedding, and the matrix in which we have these vectors are stored is commonly known as word embedding matrix. And as we will see here, kind of these word embeddings are actually really, kind of really kick off the major application of deep learning for NLP. And as I said here, so starting from kind of 2010 or so, these feed-forward neural networks, just because they really require to fix the number of context words, really slowly replaced by recurrent neural networks, and more so by LSTMs, which I'm going to talk about in a bit. And particularly in recent years, language modeling has really been a common and a very popular benchmark for evaluating and proposing kind of new variations on these types of recurrent neural networks. But as we've kind of seen in some other tasks as well, actually some of these very classic approaches, like the classic LSTM that was proposed in 1993, is actually still like a very strong baseline for this task. And in a recent paper, people have shown that if you just take a proper amount of attention and properly tune the hyperparameters in this type of model, you can actually get state-of-the-art results with a model that was proposed 20 years ago. So it's still, so these kind of recurrent neural networks are still very much a mainstay in the current NLP literature. And it's really much also an ongoing research area to better understand what these types of language modeling models capture. And I think the particularly interesting aspect of language modeling here is that even though the task is so simple, even though you essentially all you do is just using the raw form of the text and just trying to predict the next word, which is as simple as it gets. Despite of that, language modeling has really been, or kind of different variants of language modeling have really been used or have kind of been the key catalysts for many advances in the next years. So as I'll touch on in a bit, word embeddings, or kind of the most common method to learn word embeddings, word2vec, is essentially just a simplification of language modeling to make it more efficient. Sequence-to-sequence models are essentially just applying kind of the concept of language modeling, so predicting the next word for natural language generation. So for you can treat dialogue as kind of a language model prediction task. Now, like very recently this year, we've seen kind of advances. So we've used the representations and kind of the embeddings you learn from these language models actually as very successful initialization strategies that will allow you, if you use those as features, or if you fine-tune your models, that will lead actually to state-of-the-art performance on a variety of tasks. And I'm also going to mention a bit more about that in a bit later in the talk. So that was just kind of a broad overview of the language modeling part here. And now we're going to take a step of a few years, and actually there's been obviously some developments in those years, but the main kind of, as we've asked the experts, the main kind of development that a lot of people have focused on or have chosen to highlight among all kind of possible advances in the next 10 years was actually a particular paper published in 2008 by Kohler and Weston, who are now at Lingual. And that particular paper kind of introduced different advances. And one advance I want to particularly highlight here is the use of multitask learning for training natural language processing models. And multitask learning, even though it might sound, or I think some of the previous speakers have touched on that, so even though it might sound complicated, it's It's actually very simple, and it's simply it's simply a form of parameter sharing between models that are trained with different objectives on different tasks. So essentially, like as we've seen in the lectures, convolutional neural networks do a form of parameter sharing, kind of to use the useful inductive bias of spatial invariance into the models. And similarly, with multitask learning, this parameter sharing is used to induce similar representations between similar tasks and to help tasks learn each other, essentially. So this architecture that was proposed in 2008 essentially proposed to train neural networks for multiple NLP tasks at the same time. So they looked at different sequence labeling tasks like part of speech tagging and named entity recognition, and essentially had, as we've seen before, first a word embedding lookup layer. So again, where we have for each word here corresponding embedding vector for that word. And then in addition, they proposed to use a convolutional neural network with max pooling and just a feed-forward layer for modeling those tasks. And the key part here with multitask learning is that even though those models were trained separately, the word embedding layers were shared. So because generally learning, or typically the word embedding matrix amounts kind of to the biggest number of parameters in the model, because typically if you have a very large vocabulary, say 10,000 or even 100,000 words, and you want to have a kind of a 100-dimensional vector for each word, that's going to amount to a lot of parameters. And if you only have a few number of label examples for one task, it can be too expensive, or you're probably not going to get that great estimates just using those tasks. So the intuition was here by sharing these parameters between these different tasks, they can kind of collaborate in essentially learning representations that are useful, or general word representations that are useful for maybe different tasks as well. And they showed that doing this sort of parameter sharing helped in their particular setting. And so just touching on this, so this particular paper, as I mentioned, was really highlighted by a lot of experts as really one of the fundamental milestones in deep learning for NLP. And so deservedly, also this year, it received the Test of Time Award at ICML. So we mainly, besides introducing this concept of multitask learning for NLP, it also had other significant advances, like using kind of pre-training with word embeddings on a large unlabeled corpus, as well as using convolutional neural networks for text. And kind of very interestingly, at that time in 2008, when this architecture was proposed, the NLP community actually didn't pay much attention to this paper because the neural networks weren't really used at that time, and the approach here was kind of so drastically different than what people were used to that it didn't find acceptance until kind of a few years after that. And so multitask learning, actually, as I said, this was, I think, one of the most notable first applications of multitask learning to NLP. But multitask learning, kind of this idea of sharing parameters between models optimized for different tasks, actually goes back a lot further. And actually as far back as 1993, where multitask learning was essentially proposed to do different, to share the parameters in neural networks to help on kind of a diversity of different tasks. So originally, for instance, one kind of application of multitask learning was for doing self-driving cars, or for doing learning to self-drive, by basically predicting if you want to steer right, steer left, or go straight, essentially. And the auxiliary tasks that were used at that time were essentially to help to predict kind of the position of the lane. And by sharing by learning to predict the representations for this task, which is kind of, to be able to drive or to learn to self-drive a car, the model has to know what a lane is and has to know how to follow that. So by introducing this additional, very explicit supervision, you can kind of encourage the model to learn and to use representations that will capture this kind of information explicitly. And kind of this thinking behind multitask learning is really also motivates a lot of recent applications of these kind of approaches to NLP. And so generally, multitask learning, and like people are also using joint learning or learning with auxiliary tasks, kind of interchangeably to talk about that. And since over the last years, there's really been kind of often using auxiliary tasks or doing multitask learning is kind of a useful tool in the NLP practitioner toolbox. So there's been kind of a wide variety of auxiliary tasks and of settings where people have been using and that people have found to work in practice. And here I've only listed like a few number of examples. For instance, people found that you can use dependency parsing, or you can use machine translation to improve performance on dependency parsing, for instance. Another reason, like a very interesting kind of application of this, is to jointly train multilingual models. So you can, for instance, if you only have very limited data in a certain language, by jointly training models of different languages at the same time, you might be able to capture knowledge in those models that's kind of invariant to the language, and then also help for learning models on very low resource data settings. And another very interesting recent approach, which received a Best Paper Award at ACL, where they applied this notion of multitask learning to the problem of video captioning, and they basically showed that kind of learning in the form of entailment between the captions and the video jointly with this task video captioning improved results, as well as doing a next frame prediction, which is, I guess, similar to a form of language modeling in the sense that you want to kind of predicting what the future looks like. You can kind of tell the model, or can help induce kind of can help the model focus really on the useful parts of the world state, essentially. And typically, so the picture I just showed essentially just shows sharing the parameters between the word emitting layers. But since then, basically kind of arbitrary sharing schemes have been used and proposed. So you could, for instance, share all of the parameters until kind of your the neural network that processes the words, like the LSTM or so. So you could share all the lower layers of your model, and then just have task-specific objectives. Or you might only want to share, if the tasks are very different, you might only want to share the initial character embeddings, and then have different word embedding layers and different LSTMs on top of that. And also recently, some people, we've looked kind of into sort of predefining these kind of sharing schemes, because as your architecture gets more complex, there's really kind of an exponential number of ways you can kind of share across your tasks. So there's also kind of ways, similarly to what David Silver mentioned, essentially on how you can learn what is the optimal way of sharing your structures across the tasks. Because for some tasks, sharing might not actually be useful if they're too different, or if they rely on very different representations for learning. Cool. So going, okay, right. Yeah.
On the previous slide, the character, the shared information from the character neural network is just now forming just an input into the next word network.
Okay. So I didn't talk about this in detail, but so this character embedding and the character neural network, that's something that people have started to use recently, essentially, to get a representation that is more sensitive to the character level. And essentially what you do here is you essentially treat the characters in a word as a sequence as well, and then you have a separate embedding for each word, and then you can use an LSTM or a CNN to obtain a representation of the sequence, similarly to how you would use an LSTM to process a sequence of tokens in a sentence and get the sentence representation. So it's the same idea, just applied to the character level, and people have found that that is particularly useful for tasks like in entity recognition, where you might want to have something that is should differentiate between suffixes and prefixes, or just when you want to incorporate capitalization, for instance, of that, or have a lot of morphemes in your language. Right. So going here to the next point, I think this probably, if you've had any exposure to NLP, probably what most of you are really familiar with, and really what has kind of sparked the successful application of deep learning to natural language processing, which was really this notion of using word embeddings and pre-training these embeddings on different tasks. And as we've seen here, already in 2001, kind of word embeddings existed, or there was this notion of having a vector for each word. So the main kind of innovation that was brought by kind of these papers from 2013, and in particular by Word2Vec, was really that it made it a lot easier and a lot more efficient to learn these embeddings in practice, and in particular allowed scaling that up to learning these embeddings from very large unlabeled corpora, from which you can really then see significant gains if you can just increase the number of data you can learn these embeddings on, just because you require only unlabeled data for doing that. So as I've said before, so essentially word2vec here is kind of can essentially be seen as an approximation to language modeling. With the main idea, so before here with the neural network used for language modeling, we've seen that it was fed through, and the word embeddings were fed through an intermediate hidden layer. And in particular, that hidden layer just introduced kind of additional complexity and made scaling up that approach a lot harder. So what word2vec essentially suggested is that we completely remove that hidden layer. So we just directly go from our word embeddings here directly to the next state and or the next word. And in addition to that, they propose to use not the classic objective of just predicting the next word, but essentially two variants of this kind of language modeling objective. So the first one, which is called SIVO, or continuous bag of words, essentially used all of the words, all of the surrounding words as input, or as a sum to all of the embeddings together, and then just try to predict the middle word. So you have say a 5-word window or so. You feed in into your model, or you sum the embeddings of two of the surrounding words and train your model to predict the center word. So very similar to language modeling, but just a kind of a simplification or like a variation of that just allows you to more efficiently sample your training data and to really parallelize that a lot easier and really make it more efficient. And the second variant, that is the one that is kind of commonly used in practice, is called skipgram. And with that, you take your current word and you try to predict all the surrounding words. And so by doing that, it's essentially similar to, language modeling just involves predicting the next word. So with that, you just learn a representation that kind of encodes similar information to language modeling, but just allows you to make it ever more efficient, essentially. And what really kind of sparked the interest in the community and really captured, I think, the imagination of a lot of people was that these representations that were trained on a very large unlabeled corpora, like news articles or Wikipedia, the vectors or the word embeddings could really be shown to capture kind of very kind of natural or intuitive relations between the words. So people were really, there has been a lot of research and a lot of interest going into kind of better understanding what these word embeddings pre-trained on large data capture. And some of the most interesting relations are that if you project them, if you project, for instance, kind of male and female words there, you essentially the offset between male and female kind of word embeddings is kind of the same across all the variations. So you can show that this kind of embedding space captures some notion of like gender, essentially, or similarly, you can kind of learn a tense vector that allows you to go from kind of a gerund to a past tense, for instance, or also because these embeddings have been trained on Wikipedia data, for instance. So kind of the way people would use, talk about countries and capitals is very similar. So you can also get some relations between countries and capitals, essentially. And while this is kind of mostly very, very nice to look at, and I guess very of kind of some interest, I think the main reason why these have been so widely adopted in the field of NLP is that there were really people were able to show that just using these pre-trained word embeddings and using these to initialize the first layer of your model could give you essentially across a large or any number of tasks really consistent improvements. So because of that, these word embeddings are really still kind of commonly used in practice to this date, essentially. And more interestingly, because this topic was very popular, other people try to look into kind of alternate methods to learn these sort of embeddings. So people showed that essentially the thing or what word2vec implicitly does can be also seen as a form of matrix factorization, which is kind of more in line with classic approaches like PCA or SVD that have been used to also learn a form of word embedding matrix. And these approaches are kind of interchangeable or can kind of use in place of using word2vec as well. And in particular, people have really shown that if you just take or look at kind of classic methods with the proper attention and kind of tune the different hyperparameters or the different settings essentially with those methods, you can essentially get the same performance as using these neural network-based tools essentially. So one really nice side effect I think from these approaches is that they really gave us a kind of a nice perspective or a different view on classical methods really, and kind of showed that under the hood what a lot of these methods are doing is essentially the same or kind of variations of the same approach basically. And and since then, so as I mentioned, there's been really a lot of work going into word embeddings. So the original paper has, I think, more than 10,000 citations or so. So there's been a lot of interest and a lot of work in both understanding these methods better and in just applying them to a lot of different tasks. And in particular, what I also find interesting is that not only word embeddings, but also this notion of using kind of skipgram to predict your context to gain some sort of useful representations has also been adopted for other settings. So like in NLP, for instance, it has been scaled up to learn sentence embeddings using kind of a variant of the skipgram approach, but also for other domains, like people have learned embeddings of nodes and of entire networks using kind of a variant of this skipgram approach of predicting your local context. And similarly, you could also use this idea of skipgram essentially to learn the embeddings of biological sequences or of DNA, DNA strands, for instance. And another kind of, and for me personally, I think one particular, out of all kind of the open questions or all the exciting like research directions in this area, I think one particular exciting direction is that if you can also scale kind of this learning of embeddings to multiple languages, and if you do so, that allows you to somewhat learn kind of a joint embedding space between the words in different languages, which you can then essentially use if you train models on this joint embedding space. That essentially enables you to do some sort of zero-shot transfer by just using the label data in your source domain, training the model on that, and then essentially applying the model as is to your target data. And of course, that is still, it's still very simplistic because you only share the words here. So for tasks where there's lots of difference in grammar, or tasks that really rely a lot on the syntax, you're not going to get a lot of good transfer that way, but you can still get kind of almost for free in a sense, kind of a mapping of words in different languages. And people recently have essentially looked at how you can scale that to different languages using fewer supervision and using only a small number of seed lexicons, seed words essentially, or very small number of parallel resources essentially. We have a question over there?
Yes, sorry, for this one, partly more implementation. So, question, I don't know the papers yet. So, I'm guessing in this case you've got the embeddings trained separately and then you're trying to project them?
Exactly.
Or trying to find some shared space where...
Yeah, so there's different approaches to do that. The most common approach that's used these days really learns monolingual word embedding separately first using something like word2vec, and then learns essentially a projection between them in the same space. Yeah.
Can word embeddings also be used in short-form speech tags?
Yes, yeah, you can. So I mean, yeah, they can be used as well. Typically, I mean, they're used kind of as like input to train like part of speech tag or so. But yeah, people have shown that they capture also a lot of syntactic information, particularly. Cool, right? And now I think so now heading here to the next session, essentially, which from word embeddings really kind of sparked the wider application of using neural networks for NLP. And you've already heard a bit about some of the architectures that Joe mentioned that are used for processing data with neural networks in natural language. And so one key among a lot of challenges, one key challenge really here is that in contrast to images, you really want to deal with dynamic, or you're dealing with dynamic input sequences. So your models really have to scale to like kind of easily to a lot of different input sizes essentially. And the three main types of models that have been used for NLP, or that are still being used these days, are essentially recurrent neural networks, convolutional neural networks, and variants of recursive neural networks, so I'm going to mention in a second. And so with recurrent neural networks, you've already seen, or you've already heard in the kind of maybe implemented in practical, kind of the classic RNN. And as we've heard, so kind of the main problems with these with this very simple recurrent neural network is really that as the input sequence gets a lot larger, because you have to backpropagate all the way until the beginning, you really, the model can or has difficulty in remembering or in retaining all that information, as gradients in practice often either grow very small or very large very quickly. And because of that, or to mitigate that, really the main model that is really kind of used in a lot of NLP papers these days, and if you're doing NLP, which is generally like one of your go-to models, essentially is really the LSTM, or long short-term memory network, which was originally also proposed in way back in 1997, and which is really kind of can be seen as an RNN with additional gates that allow the model to modulate if it wants to kind of overwrite its previous hidden state using the current input, or if it rather wants to retain more of that information. So it's a lot easier to apply these kind of methods for NLP tasks, but also historically, only until kind of very recently in 2012 and 2013, these models were still found very hard to learn and to optimize in practice. And only recently people have really gotten comfortable and kind of more proficient in knowing how to actually work with these kind of models by using kind of additional tricks, or by just having better initialization strategies in our libraries. And and because of that, these models are really used quite a lot these days. Secondly, in NLP, also starting in kind of 2013, 2014, we've seen as well the application of convolutional neural networks. And while the inductive bias in those CNNs was originally designed for images, people have found them also quite useful for certain NLP tasks. So for instance, if you look at work in sentiment analysis, a lot of kind of state-of-the-art methods for this text classification task really use different versions of CNNs. And essentially, applying CNNs to NLP or to text is actually a lot easier than using them for images, because in contrast to images, you don't need to have like a 3, or you don't have the depth dimension in this case, but you essentially only need to consider a 2-dimensional input, essentially, where you have in one dimension the time, and the other dimension is kind of the size of your word embeddings, or of your hidden embeddings, essentially. And in this case, you only need to apply the filters, or you only move the filters over each word. So the filter size would essentially determine how much context, so how long the sequence of the words is you're going to capture with that particular filter. And then people have been typically using like similar approaches like images, using max pooling and different variants of that for applied to NLP. And with these kind of methods, it's really the advantage with using CNNs, obviously, is that because you only need to apply these filters and just slide them over your image, they're a lot more parallelizable than RNN, which you really need to process sequentially with the sequence. And in addition, kind of with the CNN, due to its filters, it kind of has a like intuitive or a more ingrained bias towards focusing on like immediate local features, which you can counteract by just using wider receptive fields, so like larger strides or dilated convolutions, or stacking more of these CNN layers on top of each other. And similarly, because these days really like CNNs and LSTMs are really essentially used kind of as building blocks in how you can construct your final neural network. So you can also combine them or stack them together, essentially to for instance, use the CNN for feature extraction, and then LSTM to deal with kind of the temporal dependency of the words. And similarly, convolutions, because of their parallelizability, can also be used inside or integrated into LSTMs to speed them up, essentially. And so another interesting aspect of language is that it's inherently hierarchical, or if you've had some exposure to linguistics, people like to construct theories or ways in how kind of syntax or different syntactic structures are formed, which is usually assembled in different types of trees. Essentially also when we kind of process language, we don't really look only at like the previous word, but actually at more kind of larger or more high-level constructs in the sentence. So it's kind of intuitive that you also want to apply or want to bias your model or use a model that can kind of more intuitively model this sort of hierarchical nature of the sentence.
Regarding a specific task, like for example, text classification, there are some kind of reference benchmark for which is better than LSTM or CMA, like some score, which one would be better?
It depends on the task. So for text classification tasks, like potential analysis, as I mentioned, CMAs are kind of used often in practice. But yeah, these days it's really they're most often, or there's not that large of a difference in practice. So often you can either use an LSTM or CMA. And people typically use or just maybe the model that has been kind of preferred for a particular task.
I'm back to this is when you explain transfer learning and multitask learning.
Okay.
I was actually looking up and you said that there was a paper that was explaining learning to multitask learn, right?
Yeah.
And I wanted to understand, so this is about is it specifically focused on the best practices, or because I looked up and you've written a best practices for deep learning in NLP, right? So is there some sort of best practice when you're trying to retrain a model? Not pre-train, but retrain it. It would vary with the kind of data type you use for the specific task. Is there a sort of
so kind of transfer. So the question was, what is if there's like best practices for doing like the multitask or transfer learning? So it's kind of like two separate settings in for multitask learning you have access to all of the data at training time, and for kind of this other notion of transfer learning, you train one task and then train on the other task kind of sequentially. And for transfer learning, I'm actually going to mention that on the last item here. And for multitask learning, people are typically doing this form of like half parameter sharing, essentially by just sharing essentially all of the parameters of the models except for the final classification sharing. Cool. So to have models that can have more. Sorry. Okay. Could you speak up a bit? Yeah, that's a good question. So the question was whether we can use different activation functions instead of the 10H here. And actually people have tried that, and there's different variants of the LSTM as well, like the GRU, which kind of tries to simplify this. But actually this particular choice or this particular configuration that you've seen here have proved remarkably resilient in that any operations that people have tried to come up with, in the end, people still found kind of the classic LSTM really to perform best in practice, which is really the reason why this very old model, almost exactly in its original formulation, is still used to this day. Because it's still, and people are kind of joking that even in 50 years we're still going to be using LSTMs as well. So the question was, why do we, what is if we want to break other values that way? I mean, so the choice of these functions is really because you want to basically decide whether to turn the gate on or off, essentially, and that's what we're stuff. And if you have more questions, we can kind of follow up on that later. Okay. Right. So we really would like to have models that can kind of more directly the architecture model this type of tree-based structure, essentially. And one or kind of a direct application of these types of models that has been proposed in 2013 or starting in 2013 is essentially to use essentially construct your models kind of bottom up the representations. So essentially all of this, and there's different variants of how to do that, but essentially you would start out with your word embeddings essentially, and then at each kind of depending what kind of structure you use. So if you use like a constituents pass tree, for instance, when you come to a high-level node, you would use some sort of composition function, essentially that would allow you to essentially produce a kind of a higher level representation that takes both of these, both of the constituents at the lower layers as input. And like that, you can essentially kind of compose the representation of your sentence kind of hierarchically as well. And people have tried out different functions to do that. And also, yeah, recently people have kind of extended LSTMs because LSTM, even though it kind of processes the sentence sequentially, you could also kind of intuit that instead of processing it sequentially, you could process it in like the form of a tree. And if people are interested in modeling trees, kind of tree LSTMs are really kind of the common method that they're using these days. And related to that, I've mentioned tree LSTMs, and there's also kind of some other methods that have been extended to deal with these sorts of hierarchies. For instance, word embeddings have also been learned on kind of depends. So rather than using or only looking at the local context, people have looked at kind of the syntactic or the semantic context to learn these word embeddings and predicting that, and found that more useful for incorporating or modeling syntactic relations in the words, for instance. Whereas, kind of extensions of language modeling, that rather than just looking back or at the immediate context, has a kind of more syntactic representation as a form of stack of the data has also been used. And more recently, people have also applied kind of convolutional neural networks to graphs or to networks in different other tasks, and very recently also using these kind of graph convolutional approaches for NLP. Cool. So going, all right, yeah.
So with the word embeddings, that's very dependent on dependencies in the language. So not all languages have that dependencies within the language. So how would word embeddings work on languages that don't have that?
So the question is how would word embeddings, or how would training these kind of embeddings work on languages that don't have like dependencies? So the dependencies here, that is really meaning kind of dependencies output from like a dependency parser, for instance. And there's kind of lots of like linguistics theory and that has gone into that, and people have developed tree banks essentially covering I think more than 100 languages essentially. So it's going to be so essentially, if you want to kind of use these kind of dependencies, you're very likely going to find that the language you're dealing with has these sort of semantic dependencies, or that you have some parser that can give you the dependencies for your data. Right. So going to the next point here. So in 2014, a framework that if you've watched Joel's talk, you've probably already heard about. 2014 kind of marked the introduction of sequence-to-sequence learning, which is essentially a kind of a very general framework of modeling or predicting not only single labels or not only labels for each task, but modeling an entire output sequence essentially. And really kind of the most the application really that has really sparked and really showed the success of this sort of methodology has really been neural-machine translation, where in recent years we've really seen kind of existing statistical, like enormous architectures of statistical machine translation systems having been replaced by these comparatively or conceptually simple neural network-based architectures. And sequence-to-sequence learning is really like very simple in its formulation, in that you again have a sequential model, like an LSTM typically, that processes an input sequence, one word at a time, if we're dealing with natural language tasks here. And at some point, once the sequence finishes, or once we reach kind of an end of sentence sign here, the model then starts predicting the output, and you kind of feed in, or typically what people do is you would feed in the predicted output of the model again as input in the next time step. And this way the model can essentially effectively be trained to do any sort of sequence prediction task. And these kind of what you use as the encoder and decoder is really very interchangeable as well. So you can use your kind of preferred network of choice for those tasks. And really these days, sequence-to-sequence learning is really the go-to framework when it comes to any sort of natural language generation task. And the The interesting thing is that it's even kind of goes beyond just the idea of natural language generation, in that the output or what you want to predict cannot only be conditioned on just a natural language sentence or an input sequence, but because it just requires you to have essentially a representation, a hidden state that you can use for generating your output, you can condition that on any other representations or hidden states that you can get from processing other forms of input. So for instance, like one great example of one application is people have used that for image captioning, where you could use your CNN network of choice to process an image here with your kind of inception-like model, and then use that as input or as conditioning for your LCM, and then start generating a caption of that image in practice. And we have really been showed like very cool and very surprising or very positive results with this type of methodology for this task. And even going beyond that, sequence-to-sequence models have even been shown to work for tasks or to be applicable for tasks where there's more structure in the output. So in NLP, we have a lot of tasks like dependency parsing or constantly like different parsing tasks, where you try to predict not just a sequence, but actually a tree or something that have actually been shown to be able to transform into these sort of sequence-to-sequence models, and using like for consistency parsing, for instance, where you want to, given a sentence, predict its syntactic structure. People have really found that instead of predicting this parse tree, essentially you can just linearize the output here. So you can just train your model to predict essentially a sequence where kind of brackets indicate at what layer of the tree you are. And if you train your model on, if you can generate or if you have enough data to train your model on that, you can actually, by training your your model to produce this very stupid output, to actually improve upon state-of-the-art approaches where people people in NLP have spent a lot of time kind of engineering their particular parsers. So this really has been kind of one approach that really, even though it was very kind of very simple or stupid, like dumb application of this kind of approach to a different task, really showcased very convincingly really the wide applicability of this sort of paradigm. And similarly, because the encoder or the decoder you use are really very are really task dependent and really interchangeable. So typically people would use RNS for those. But also recently people have looked into all kinds of different other encoders and decoders to use for these architectures, which has mainly been driven by advances in machine translation, because in those kind of cases there's a lot of training data and just a lot of people interested in working on these kind of tasks. So recent models, for instance, Google showed that, or used in 2016 for their Google Translate model that was deployed subsequently, very deep LSTM of kind of 8 different layers for the encoder and the decoder. And more recently, we've seen also CNNs being used as encoders for sequence-to-sequence models, as well as a transformer model, which I'm going to talk about a bit later, and also a combination of LSTMs and transformers. Am I doing it on time? Okay. So in kind of the topic or in the line of neural machine translation, I think one of the kind of most important advances in recent years has really been the use of attention. And attention is really something that started in machine translation, but then has really found wide application in other types of tasks as well. And attention really, even though kind of the term really sounds very abstract, it can really be seen as essentially just using or learning kind of a weighted combination of your, or looking essentially, so in neural machine translation, when you want to produce the next word, the earliest sequence-to-sequence models have really been hindered by their reliance on encoding all of the sentence in just one, so they've really been hindered in having to encode the entire sentence into just one vector here. And attention, which really worked as a bottleneck in the beginning, and attention really allowed these models to look and consider all of the hidden states of the sentence it has seen before, which then allows really improved performance in those cases. So attention is really, so given the current hidden state of the model, it essentially allows you or measures the similarity of that hidden state with all previous hidden states of the model, and essentially allows you kind of to learn a weighted combination of those, and and like that essentially focus on the past hidden states that are really most relevant to your current prediction. And for attention, there's been different forms of attention, or different ways you can kind of learn the parameters that have been proposed for that. And attention really has been, or is widely used in practice. For instance, people have used that for constituency parsing and a lot of other tasks, like looking at the text you've read for answering questions about the text, and in particular for image captioning, for instance. So attention, because it just requires the use of hidden state representations, is not only constrained to using it in NLP. So people have also used it for image captioning, where you look at the kind of representations or the states of an image. And in that case, it can actually give you some insight or a bit more interpretability into what the model is actually predicting, by essentially allowing you to look at which parts of the input are weighted most prominently. And here, so when a model given image wants to produce a caption here, you can essentially show that the state or the part of the input the model really looks at when it wants to predict the word frisbee is actually here the frisbee that the person is throwing. So you can really get at least some rough or very rudimentary approximation of that the model is actually looking or doing something reasonable. And attention, besides that, is also not only restricted to looking at kind of the previous sequence. So recent models have really tried to apply attention also just to look at the surrounding context, which is called self-attention, and in particular the transformer architecture, which you might have heard of, which is currently the state of the art, essentially for neural machine translation, heavily relies on the use of self-attention in its layers. Cool. All right. So I'm getting a bit short of time, so I'm just gonna take the next ones are kind of shorter anyway. So just going here, so attention essentially, because it really allows you to look back at the previous sequence, can essentially be seen as a form of fuzzy memory, in that you essentially want to determine, given the previous states, what is kind of most relevant or what you kind of most want to remember. And related to that, kind of with some very popular methods like the neural Turing machine and end-to-end memory networks, people have also looked at the use of more explicit memory to better store or to encourage the model to better remember useful information for making predictions. And these types of models really work very similar to attention. So they have a sort of explicit memory that is represented by hidden states. And the retrieval then typically is based on the similarity between different states of that memory based on the current input in a sort of attention-like fashion. And there's different variants of that. So for instance, the end-to-end memory network would process the input multiple times and kind of update the different hidden states or its memory essentially, while the neural Turing machine, kind of in this notion of having a tape, would also add kind of an additional location-based addressing that it would allow it to look at or to focus on particular slots of its memory, which can then allow it to learn certain simple algorithms like sorting, for instance, that really require on accessing certain parts of your memory in a certain order. And memory really is something that kind of is a very general concept as well. So really, I think a lot of people are thinking about that these days as well. And it's it has been applied in different ways. As it's essentially it can essentially take different forms. You could use it or to populate it from a knowledge base or based on unlabeled training based on your data. And all right.
This question, the whole technology of associative memory, is that ever sort of making a comeback or not?
Sorry, which?
Associative memory, like the old style memory from many years ago. Is that sort of related to this or not?
So the question was whether kind of old approaches like associative memory are related to these sorts of approaches or making a comeback. And I think some of these methods actually kind of motivate or use or kind of compare themselves to using associative memory or kind of liken that in a similar fashion. So I think you can not sure if it's, so I don't think the exact method is used, but a lot of these kind of approaches really take inspiration from these sort of approaches, and really in the way they kind of create or try to access the memory is really, I think, inspired by more kind of classic approaches. Cool. So now we just skip from 2015 essentially to kind of the most, so this year, and I think this year, I think we've seen, or particularly in recent months, we've seen kind of a lot of exciting developments in terms of using pre-trained language models for transfer learning in NLP. And in particular, so one motivation for that is that before, as I've said, pre-trained word embeddings are really kind of widely used in practice for initializing the first layer, but the downside of using word embeddings is that they are really context agnostic. So you maybe have some general relations between the words, but you still, your model still needs to learn from scratch how to compose words in practice, maybe how to disambiguate words based on context. So it really still plays a big burden on the model for actually learning kind of the hard part of natural language processing. And kind of going from, and as we've seen before, language modeling or predicting the next word essentially allows you to induce representations that capture some of this information. So language model can kind of really, or has to capture really how to compose or how to predict the next word essentially, and information that is useful to that. So recently people have found that instead of just initializing the first layer of the model, using embedding from language models or fine-tuning a pre-trained language model on your target task actually can give you very significant improvements on a wide array of tasks. And one particular approach called ELMO here, that won the best paper award at NACL, really has kind of extensively evaluated using language model embeddings as fixed features into the model, and has kind of shown improvements across state-of-the-art on a wide variety of very diverse tasks, like predicting entailment, doing an entity recognition, which is a very classic task, doing question answering, co-reference resolution, semantic role labeling, so a diversity of different tasks. And in almost all cases, you can see very significant improvements using these additional language models as features in your model. And finally, what I think is kind of a very, or I think is most promising in my mind really, is that using this form of pre-trained representations really enables you to do a lot more sample-efficient learning. So you, in practice, require a lot more data to get reasonable performance. And in addition, this pre-training step only requires you, or training this language model intrinsically only requires the use of unlabeled data. So it's something that can be really, or I think will really help NLP be a lot more widely used for a lot of other, in particular, low resource languages.
I just wanted to check. So the first time I came across kind of idea of pre-trained language models was in your paper with Jeremy Howard that you published a bit earlier in the year. But then I saw recently that someone had actually kind of applied them kind of in the context of, I think, like a language model and then using an autoencoder to do a kind of pre-training set in 2015. Yeah. Why do you think that didn't kind of catch on earlier? Like, why did it kind of only burst onto the scene in 2018?
Yeah.
What's your explanation?
So the question was, why, so there's been, the earliest application of using these sort of language models for training was in 2015, and they already showed improvements. So the question was, why hasn't that not been adopted earlier? So why are we only talking about this milestone now and not in 2015? And I don't think there's like one answer to that. So I think there's maybe multiple reasons. So I think both kind of in 2013, or 2013, and then afterwards the wide and the very easy accessibility of word embeddings really, I think, drew a lot of researchers in that direction and really monopolized a lot of interest. So I think, and because people at that time were already like still trying to understand word embeddings, so I think a lot of people might have gotten interested in language models, just had like this very low-hanging fruit of using word embeddings. In addition to that, I think in 2015, it was also still a lot harder to train RNNs or LSTMs. So you still just had, I think in 2015, still like just TensorFlow, I think, getting started. And it was just not really easy yet to use these kind of methods. And then I think thirdly, at that time, so that paper only kind of showed results for classification, I think. And I assume a lot of members in the community at that time probably were skeptical whether these language models really were useful for more complex tasks like modeling co-reference or doing question answering. Right. And yeah, so I think like the most promising direction is really the application to low resource languages. And then finally, because we focus on 8 kind of milestones here, there's like 3 other ones which I think is kind of relevant, which are mainly the use of character-based representations, as I've kind of touched early on before. Similarly to computer vision, people in NLP have also started using adversarial learning, whether that is using adversarial examples to probe your models, using kind of similar generative adversarial type approaches for kind of language generation or optimization. And then finally, people in NLP also have started using reinforcement learning, although I think that's mostly been successful in certain settings where there's either kind of very strong temporal dependency, like when you want to have some environment or some state that changes, or when you have when you don't know kind of your true objective function essentially. So if you have like something that you actually try to model, like bleu or rouge, but that just imperfectly but that is non-differentiable. And with reinforcement learning, you can just more easily directly optimize this with the objective. Right, cool. So this was really the kind of a very brief, quite fast overview of some of the milestones, and we're going to make those slides available offline as well, so you can check the references if you're interested.
Okay, so I was actually asked for this part of the talk to talk about the big open problems in NLP, and because I was a bit lazy and I'm not completely qualified, I just called in the help of the amazing panel here. So Sebastian, you know, Bernard is from Prekelt, Jade is from Retro Rabbit, Emoji is from GitHub, and Stefan is from this relatively successful software company in London, DeepMind, something like that. Yeah, so we really want you to walk away with a sense of what the big open problems are in NLP. And to do that, because I really didn't feel like we're completely qualified to do this, we also called in the help of a whole bunch of experts across the world. Yeah, so we did this thing that I think is pretty cool. So what we did was we emailed around 50 people, experts from across the world, and asked them what are the biggest open problems that you think is the most important thing to work on? What are the things that you work on at the moment, and what's the big questions in NLP for you? And you'll recognize some of the names here. We had amazing responses from a whole bunch of people: Joshua Bengio, Chris Dyer, and a whole bunch of really expert NLP researchers. And we wanted to share those answers with you. And then what I'll do is I'll basically summarize the most important responses that we got. And the panel will then help me to talk through some of those thoughts, and then to also answer some of your questions that you might have. Okay, so we asked the experts, what are the 3 biggest open problems in NLP at the moment? We went through all of the responses from everyone, and we kind of identified actually 4 big open problems that people are working on. The first one is natural language understanding, natural language processing for low resources scenarios. Sorry, I can't say that. Low resource scenarios. So that's both low resource languages, but also settings where you just might not have enough data, even if it might be a high resource language. The third one was reasoning about large or multiple documents, which is a very, very tough task. And then the fourth one is data sets, problems, and evaluation, which was highlighted by many of the experts. So I'll just step through these. I'll kind of highlight the big trends that we saw, and then I'll ask the panelists some questions, and you can also ask them some questions. So the first one is natural language understanding. And many of the experts said that basically for any NLP task, this is the biggest problem that we need to crack. Some of the experts said that basically none of the current models really have a true form of natural language understanding in the way that humans have. They said that very often these models basically are just doing some like brute force form of pattern matching instead of having a real understanding. some of them raised the question of what biases and structures should we actually build into these models. The word common sense was in, I don't know, maybe 70% of the experts mentioned this word of common sense. If you ask a robot, get into a car, right? Say that's a natural language expression, get into the car. For us, it's really intuitive, right? But for a robot, they need to understand that there's this thing called a car. They need to understand that to get into the car, they need to open the door. There's a handle, right? And then they need to execute that action. It sounds so stupid to us, but that idea of common sense about knowing about the world is something that our systems are lacking. And then almost all the respondents mentioned dialogue systems, what some people call chatbots, as being like one of the biggest things that we need to crack. Just to give you an example of, this is from one of Percy Liang's papers. Just quickly read this article. It's about Nikola Tesla. So I'll just read it from the top. In January 1880, two of Tesla's uncles put together enough money to help him leave Gospic for Prague, where he was to study blah-de-blah-de-blah-de-blah. Okay, now I ask you the question, what city did Tesla move to in 1880? Prague, right? Okay, cool, great. You're all human, so you get the ground truth answer, great. State-of-the-art question answering model trained on data to answer this type of questions, trained on something like Wikipedia, answers Prague. Okay. So, right, we've solved AI. So, what Percy Liang did was they actually said, what happens if you do something like this? Okay, so there I've got a paragraph. In January 1880, two of Tesla's uncles, blah, 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 Prague, blah, 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 blah. Okay, then right at the end there's the sentence, Tadakutsu moved to the city of Chicago in 1881. What city did Tesla move to in 1880? What's the answer? Okay, so there's, okay, most of you are human. You get Prague, which is the correct answer. Okay, some of you make the same mistake as, okay. So actually a model, the state-of-the-art question answering model predicts Chicago here, okay? Just okay, apart from Jeannie, most of you got it right. Okay, so they actually have, it's a very cool paper where they have an extremely simple way of generating or adding these adversarial sentences to a bit of text. And then it just breaks these systems. And if you had any form of common sense, you would get this right. Yeah?
Was there some confidence score to that answer?
You'll have to go and read the paper. I'm not sure. I'm not sure. Kevin Gimple, I know this is a long quote, but he just gave an amazing answer, and I'll just highlight, it's more for the record because we'll put these slides online. But he basically said that he thinks that the biggest thing that we should do is to develop systems that read and understand text the way a person does, by basically building a model of the world with the agent's objectives, and kind of the setting, the relationships, the goals, and the desires of that agent in a similar way that humans have kind of understand the world. So he really argues that to do true natural language understanding, we need to kind of have an agent that understands the world exactly a way a human does. Okay, so that's the first open problem, natural language understanding. And what I'll do now is I'll just I'll ask the first question because I've got a microphone. And I think I'll direct this question to Emoji. Do you actually agree with this sentiment that to achieve natural language understanding, you really need to build in into models kind of a way that the person would solve these type of tasks? I think also following on from David Silver's lecture, if you just saw that, he was actually arguing in reinforcement learning for very much the opposite thing, right? He was saying like, let the data speak and only let the data tell you what to do. Where actually a lot of our respondents said that you should actually build in knowledge of the world if we wanted to understand natural language understanding or achieve that. So what would you think? Do you agree with this sentiment that we should build in?
Can I just clarify? Is the question whether we should include sort of what inductive biases that we think are how humans process language, or is the question that our learner should be exposed to the same kind of rich sensory environment from which humans learn?
Whichever one you like. I think both of those questions are actually important. So if you have you can pick your question.
This is a hard one to answer for me because we want to achieve natural language understanding. If we want to achieve natural language understanding as a way of investigating how humans learn, then yes, we've got to build something that is akin to how humans actually acquire language and process language. Now, the question is, what is the evaluation? Do we truly know how humans acquire and process language and turn that into knowledge? I don't think we do. So if we build this thing, how do we know we've actually replicated? What we can see is that it can talk to us as a way and reason, but we don't actually understand the true mechanisms by which humans acquire language, turn that language into knowledge, and speak it back out. Now, in the quest of building machine learning applications, the statistical-based approaches have somewhat worked for us. I was saying this earlier, I was in a podcast with Nando and said that I think this is one of those areas where we're going to have to do something like program synthesis, where we have our statistical-based approaches that we've been using, and then we go back on top of that and go back to what we did in the 80s with this idea of things like FrameNet, Psych, all these things that we were collecting knowledge of the world, this big things that we've somewhat abandoned. We go back and bring them in now. We should revisit them and merge them with our statistical based approaches. Perhaps then we can then infer that the robot will be able to know, oh, a car is a vehicle and it has handles and has all that kind of stuff. And so maybe that's where we need to go. I don't know if that will still help us understand how humans acquire language, but we'll be getting further in solving the problems, that applications of natural language understanding.
I think that was an amazing answer. Okay, Stefan, you grabbed the mic very quickly. Do you have also have an opinion?
I have a short opinion on that, and the first one is I agree that's possible, probably a very good approach. We have this information available. We have structured sources, knowledge sources available. Why not use these sources? It's the same argument to be made for why use evolutionary algorithms for optimization when you have the gradients available. But on the other hand, I also want to say that humans learn language through experience. We learn language by being embodied in a certain environment where there are rules of physics, where the world works in a certain way, where we try to survive. And through experience and through interaction with the world, we learn the actions and the meanings associated to objects and their semantics, which allow us to stay alive biologically. So the other side of that is to say, you could argue that there exists a single learning algorithm, which when you endow an agent with this algorithm and you have a sufficiently rich environment within which to embed this agent, and we find the right reward system or reward structure for these agents, then they could discover this from the ground up. Now, the kind of environments that you need in order to do this, the kind of compute that you need in order to simulate this is tremendous. I mean, if you look at AlphaGo and the kind of computational infrastructure that was needed to solve a little board game, and you extrapolate that to the amount of states that exist in the real world, I think personally that we are headed in that direction. A lot of people agree that we need to head towards embodied agents learning in a sort of simulated environment, but we shouldn't underestimate how much infrastructure and computing power that would actually take in order to get to that point.
Okay. Do any of you can either have a comment about natural language understanding, maybe you have a perspective on this, or you can ask a question to one of the panelists. You just need to shout out, or I can repeat your question if you're in the front row.
I was just going to ask, as far as this is concerned, how much of knowledge in neuroscience are we leveraging? Because I think my understanding is as human beings we still have an innate ability from evolutionary biology to process and learn language, and kids can learn a lot of languages at a young age. And so if we try to build a system that can understand language, how much of that knowledge are we leveraging from neuroscience? I think that's something that was touched on, but I'm just wondering how much of that are we incorporating in
So the question is basically how much of knowledge about neuroscience are we incorporating into our models, or how often do we look to neuroscience or maybe cognitive science even, which is kind of like the level up, how much of that are we explicitly building into our models? So any of the three people that didn't speak, do you have an opinion about this, or do you know the answer? Sebastian, you spoke a lot, okay, but...
So I don't have a background in neuroscience, but I think, so in general, I think it's a very useful strategy to kind of look to like cognitive science for inspiration for our models, or let us be kind of inspired in the way we kind of design our architectures. So while I don't think it's necessarily the best approach going forward to really try to like model the brain or try to model exactly our understanding, I think still kind of the way our at least like cognitive theory describes things is still a very useful guideline that we can incorporate. For instance, whereas I mean the current way like LSTM works, or the current LSTM model is very heavily biased towards more recent inputs. So and as I mentioned before, typically when we read, we don't really look or don't just remember like the last student state or just like the most recent words. So in that direction, for instance, it would be very useful to have models that have kind of a more high level or more like syntactic or kind of more hierarchical notion of this sort of memory. And there's been approaches in this sort of direction. So kind of in this range of like thinking fast and slow, we have like a fast kind of intuitive notion and something that is more reasoning that has kind of been applied to some reinforcement learning problems as well. So I think people are very much kind of taking those ideas into consideration.
I have one last thing.
Yeah.
This is one of those environments where interdisciplinary expertise actually becomes very useful. I did a PhD in computer science education, basically cognitive science, studying how people actually acquire computation. And there's a lot of work of Vygotsky and Jean Piaget. A lot of the work has been done. So we need to go back and study that work and bring the mathematical realizations of those approaches of acquiring language and acquiring knowledge, and then demonstrating or running experiments to see if they're useful or not. Because we know certain things about the process of human beings acquiring concepts, getting disequilibrium, and then getting re-equilibrated back. So we know all those things, but it requires interdisciplinary expertise. So I urge all of you, interdisciplinary work.
That was actually something that a lot of the experts also said. I'll show, I don't want to jump ahead, but I'll show a quote from Felix Hill just at the end, where he says exactly this. He basically says, don't go to NLP conferences, go to CogSci, the Cognitive Science Conference, which was an interesting perspective. Can I go on to the... yes?
I think a few people at the Indala so far, Sebastian, Cho, Nando, have spoken about the important use of NLP in Africa because of our huge amounts of different languages that we have for neural machine translation, for example, to solve a lot of problems. So I was wondering if any of the panelists have any ideas about current developments in that direction that are happening here in Africa.
Okay. Don't answer that question. Okay, I'll just go on to the next problem. NLP for low resource scenarios. Very good. So I'll summarize this and then someone will answer your question, right? It's also my first question. So a lot of the respondents, they said that NLP, it was surprising because these are guys, they don't necessarily live in Africa, or they don't live in countries with low resource languages, but almost all the respondents mentioned low resource languages as a very important avenue for NLP. Generalization beyond the training data, this is not something that's specific to low resource scenarios, but it's something that's very important in low resource scenarios. But Joe also mentioned at the start of his talk, we have the setting where we're training our models on one set of data, but we're really not interested in what happens on that set. We're really interested in this kind of training scenario where the data comes from a completely different, well, not completely, but a different distribution during test time compared to training time. And a lot of the respondents mentioned that. Sebastian gave a really nice overview of some of these things. Some of the respondents mentioned domain transfer, transfer learning, multitask learning as a way to leverage labeled data on some data sets and then apply that to maybe data from an unseen language. Learning from small amounts of labeled data. There were also things like semi-supervised learning. So that's where you maybe have a large data set that's unlabeled and together with a small data set that has some labels. Okay, and then there's variants of that. Weakly supervised, weakly supervised, distantly supervised, lightly supervised, minimally supervised. Okay, if one of the panelists can give a definition of all the differences between these, that would be great. Unsupervised learning, basically learning from unlabeled data. I think all of these things are very important, specifically for us. Maybe I can just mention this very quickly, but actually Sebastian mentioned some work like this, where you maybe have you have an embedding space in English trained on data in English. Here you've got an embedding space in Italian trained on a completely different data set, right? So you've got this non-parallel English and Italian data, and then what these authors did, it's a great paper at iClear, they basically learn a mapping that morphs the two embedding spaces on top of each other, and by doing this you can do essentially unsupervised word translation without actually having parallel data in the two languages. I just like this paper, so I'll mention it very quickly. These are authors from MIT. What they did was they actually have one embedding space which is spoken embeddings, and then they've got another embedding space which is text embeddings, and then they map the two on top of each other. So this is settings where, imagine you've got a large corpus of speech and it's unlabeled, and in the same language you've got a large corpus of text, okay, but they're not parallel. Then they don't have anything to do with one another. Can you actually learn a spoken embedding space, a text embedding space, map the two on each other, and essentially do a form of unsupervised speech recognition? Okay, this is very early days, and there's a lot of caveats in that paper, but I think it's pretty cool. Okay, sorry. Maybe we should answer. Wait, what was your question again? Okay. So, can I ask this question? Is that okay? Just check that question.
It's coming.
Yeah, that's fine.
Is that fine? Okay, so the question, I'm going to direct that to Bernard. Is it necessary to develop specialized NLP tools for specific languages, or do you think it is enough to work on kind of general NLP? And I think maybe specifically for people in Africa, for us, is it more important to kind of pursue the grand goal of like general NLP on all languages, or do you think it's worth building specialized tools?
Well, to come back to a point earlier, there's lots of argument to be made that the visual system kind of evolved first, and then we acquired language. So there's a good chance that there's a universal commonality between languages. So I like the idea that Joe presented as well as of having this universal language model. I mean, you just have to train the encoders and the decoders for all of the different languages. And the challenge is then in getting enough data for those. And of course, he also showed that you can attempt to train that universal language to make that position for unreduced languages a bit quicker.
Does that satisfy you? Not really.
I guess I'm interested in if there are any interesting things happening at the moment tackling this problem.
Apparently not. There.
So it is a problem of data. There are people in the room that are actually actively involved in collecting data under the Creative Commons clause. But I believe I haven't actually done any work on that. I believe Stephen, you've done some work on that.
I will just say I have just one comment. To answer your question more directly, there's not enough work on it, and to just add my opinion to the topic in general, I think it depends what task we're looking at. When we're looking at low resource scenarios, when we're looking at domains where they're, like for instance in Africa, I learned today that there are between 1,500 and 2,100 languages in Africa. And just Nigeria alone has 500 languages. It's incredibly rich and diverse. If you look at the task of something like topic classification, anything that is bad with words, then we have techniques to deal with that. But the issue is sample efficiency of these methods. Is how much data do we need to actually make these techniques work? I did some work on cross-lingual embeddings, and this is exactly what Sebastian showed, where you try to learn embeddings in one language, and you try to learn embeddings in another language, and you try to map them into a common space. These methods work quite well, and in fact, you don't need a lot of labels, supervised data. You just need a few pairs of words between the two languages that are known to be the same words, so you can take them from a dictionary, or you can ask someone to give you a list of 100 or 200 words that are the same. And then you can align these spaces, and you can align them sufficiently well so that you can actually do things like document topic classification. You can do things, for instance, like polarity at a very sort of rough granularity. But you cannot do things like machine translation between the two. And I would argue that, I actually can argue against myself both ways, but on the one hand, I would argue that bag of words gets you very far.
Yes.
There's a lot of things you can do with stupid models.
Yes.
But what we're driving towards, the question of natural language understanding, things like machine translation and question answering, it is incredibly hard to build systems in the languages where we have a lot of resources and then transfer them efficiently to the low resource setting. So I hope that answered some of the questions.
I'll stick with Stefan. I told you I'll ask this question beforehand. But I think this is something that someone once asked me and I didn't quite know how to answer. They said something like, since there is inherently only small amounts of text available for under-resourced languages, the benefits of NLP in such settings will also be very limited.
Okay, so I vehemently disagree with that statement. And I think the reason why I will describe it as follows. I think as practitioners of NLP and of machine learning, we tend to think in an information theoretic way. We tend to think we want to build our systems in order to maximize the likelihood of a data set, in order to improve the benchmarks, the results on some kind of task. But take a step back and philosophically speaking, or just socially speaking, why are we actually working on these problems? We are working on these problems because we want to build systems that break down barriers. That's really what we're working on. We want to build language processing systems in order to enable people to read the news in their own language, even if it wasn't written in that language. In order for people to ask questions related to health when they don't have access to a doctor, but we can build a question answering system. So when you look at it from that point of view, then it really honestly doesn't matter how much resources is available in that specific demographic. It's about helping human beings in that demographic solve their problems. So it really depends on how you define benefits. I kind of want to take a leaf out of Bill Clinton's book here and say it depends on what the definite is. It depends on how you define benefits, but the way that I define benefit, I think it is some of the most important areas of research is how to build systems that work in low resource setting. And the other reason for that is, as I just mentioned, yes, if you look at one individual language, there's not a lot of data for this, but it's a long tail of low resource languages. The bulk of the data or the people that speak languages actually speak sort of low, what we would classify as in the low resource regime. So we really need to find a way in order to make our systems and language processing systems work for in that setting.
Jay.
To kind of add to that, I find it almost ironic that we focus on in NLP when a large amount of the research around the world, they have been focusing on like the languages with lots of data, because those are the languages that are well researched, well taught around the world. So the languages we really should be focusing on are the ones that aren't, we don't have those vast data sets. So, and I have seen, what's great is that the Endavi, you are seeing there are pockets of people with papers actually doing work in that sphere, making little bits of progress, and also agree with the sentiment that like, is it, the value that a bag of words can add here will beat what machine translation will add to probably the rest of the world, right? And you start putting those systems and deploying them, you'll see much more impact here to like a whole lot more people than perhaps just giving a cool new tool to people in the EU or in the States. Yeah.
I think there's a comment.
Yeah.
If I can sort of give a minority opinion in opposition to the two previous perspectives. I've been working on very similar problems in speech processing for the past 15 years. And we find that you do a lot of work to make systems work for these smaller languages, but the users are often more motivated to actually access the major language systems. So in a way, you can either do a lot of work on Chivenda and isiZulu and lots of these languages, or you can do a lot of work on say, dialect or accented English. And it turns out that the users are often much more motivated to use a system that's in English if it works for their dialect or accent than having it in their own language. And so perhaps an alternative way to reach that same social impact that Stefan spoke of is to help people to access these English systems and all the information that's available in English and German and Mandarin, these major languages, for people who are not that fluent in those languages, rather than to build systems in those small languages.
Did you guys on this side catch that? Just not? Okay. Before this session, I told Stefan I really like some conflict on a panel. So,
that's what I'm good for.
Yeah, thank you. Bukosi,
yes.
Do you want to take up the fight?
So I don't have 15 years. Something I stumbled upon last week and I've been working on in the last 2 years. And given even again places like South Africa and most of the African countries, for me, some of the passion that I have for NLP comes from historical preservation. So the things that are going to come with either translation or understanding is going to being able to actually understand people where they are, right? Because there's still a lot of things we don't understand about each of our cultures, and some of these do get lost even in the literal. We will go into English and they get lost in that translation. How do we find ways to do that? Yes, there are still the work to build applications that we think will be universal or classified or cluster and all those things, but there will still be the use of these other things, and not just bag of words will get you far. I think that's a given. Yeah. But there's going to be these other things that also we can actually use these other methods, and I think that's a thing of people shouldn't stop working on it because bag of words will get you far. So yeah.
Yeah. Jeannie, and then there. Yeah, so Jeannie said that mother tongue education is really important, and if you kind of fix mother tongue education early on, then that might alleviate this kind of dependence on learning another language like English later on. There's a comment there.
Yeah, to go back to when you were saying earlier that there is we hear a lot of intention during this Indaba, like, oh, this should be applied to those local problems, right? But then when we are asked what are the practical applications you've encountered so far, trying to solve that, we're unable to answer. And maybe it's intrinsic to the community or to the way we publish in academia that we want to improve the score, and so French and English and Deutsch or whatever are going to be the languages we try to solve. But how do we incentivize the community to address those problems? Because there's a lot of good intentions, but there's not a lot of work.
Did everyone get that? Can I repeat that? So I'll paraphrase a little bit. So I think what you said was that often in academia we're incentivized to do well on, for example, English-French translation, because if you write a paper that gets a 500 blue score, then you'll get seen. You get kind of incentivized that way. But we don't have that same incentive necessarily for doing that same type of thing on low-resource languages, maybe spoken around in Africa.
I have just a quick comment on that.
Stefan, you're speaking way too much. No. Go.
Just a quick comment. I don't think that the incentive doesn't exist. I think that the skills don't exist in the right demographic.
Yeah.
People have problems, and if you give them the skills to solve those problems, they will solve those problems. So what we may need to focus on more is teaching people skills like machine translation, neural machine translation, what we're trying to do right now, and then people will apply these in their own setting to their own problems. It's the academic, the kind of evaluations, the kind of progress that we pursue in academics is not necessarily, I agree, it doesn't necessarily relate to all of these low, individual sort of low resource settings, but I think if you empower people with the skills, then they will actually develop the methods to solve their own problems.
Yes, we are.
So the other thing I was thinking about, because at some stage I was like, I would like to work on low resource language, and I went out to find data, and I emailed a whole bunch of research groups, and none of them got back to me. And I thought, oh, maybe Open Africa will have something, because they've got loads and loads of data sets. And I went online there, and you can go look. And I searched for ages, and I couldn't find any open data sets for low resource languages within Africa. And I thought, can't we solve that? And maybe if we make that data more easily available, we'd get more people incentivized to work on it, because there's not such a high barrier to entry of just trying to get. I hear loads of people, CSIR's got lots of data, UNISA's got lots of data. I'm at the point where I'm just going to go scrape government websites and different translations to just get the data. But I think people have already done that, and I think what we should do is just go put it on Open Africa, and that would incentivize me, because now I can just go do it.
So maybe just one last comment on this. There is actually data available. I don't know if you want to say something.
Yeah, I'll say something about that in 5 seconds. Okay. Okay. So I think I'll just move on to.
Okay, yeah, I just want to add a brief note to that. So while I think going forward, how we can reduce reliance on having huge, thousands of label examples for training, I still to add to that. Essentially, I think it's really paramount that we have at least it can even be small, just very qualitatively labeled test set. So I don't think we even gonna need training a lot of label examples. It's just something we can test our models on, some unlabeled data maybe in that language from which we can learn as well. And I think that would really incentivize a lot of people kind of working on ideally for a task that is really impactful as well as practice.
Perfect. Okay, I'll just move on quickly, because I think you've actually touched on one of these things. The third big open problem. I'll just mention this because it relates very much to natural language understanding. So the third open problem that a lot of the experts mentioned were reasoning about large or multiple documents. Basically, if you have very large contexts, how do you figure out what's going in text documents? How do you summarize? One of the experts also mentioned spoken documents, which is even more difficult. And then again, multiple people mentioned common sense. This was just one of the examples. So there's this narrative QA data set where I won't go through this example completely, but it's basically if you read a whole movie script, can you then answer relatively simple questions about that movie? So don't read the stop bit, but you can see there's this little snippet from Ghostbusters. It says something like, Dana says, "Thank you, Fred," blah, 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 blah. Makes a funny face at the baby Oscar, a very cute 9-year-old boy, blah, 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 blah. It goes on, and then the system is asked, how is Oscar related to Dana? And it's actually like, if you only have this snippet of text, that's a very, very tricky problem, right? If you just have this natural language text where Dana is discussing something with Frank, and she kind of turns to the boy Oscar, it's very, very hard for our systems to be able to do this type of thing. But it relates to natural language understanding. So I'll just kind of skip this one because I wanted to get to the last one, the Rod's open problem, because you guys have figured out the big open problem. Data sets, problems, and evaluation. And I really liked Mikkel's response. He basically said it's really important to properly define the problems themselves. He said, figuring out what the problems are is is essentially the biggest open problem. Okay, and then he said data sets and evaluation. Alta de Waal, who some of you might know, she basically gave a one-line answer, which was fine. She said basic resources. That's the biggest thing, the biggest open problem that we need to crack. And then this is what I think Bernard wanted me to mention. So there's this big initiative, SADILAR, South African Center for Digital Language Resources. You can go on this website and they've got resources for many of the languages spoken in Southern Africa, speech data, text data, and that can be really, really useful to start to build these type of systems. I think that is very part of the incentive for doing this this type of research.
Yeah. Like I said, we're waiting for word embeddings for the languages, please.
He wants someone to get word embeddings for him for all the languages. Okay.
Just to add to that, I think like Facebook, they released a while ago actually word embeddings for more than 100 languages.
No, that's not on Wikipedia. It's not that great.
Because that's what I was going to say.
Yeah.
Sorry. I was going to say now that it's the wiki issue.
Wikipedia.
Of saying, like, you know, looking at my language song like Tswana is probably much more available than Xitsonga. So I wouldn't trust as much those embeddings, but there is an opportunity. I think maybe talking to a couple of people here after this is we know I think SABC and use programs are supposed to be transcribed. I've been trying to get them to open up their data, even if it has I have no I get no benefit from it, but that will be a large resource that is on there because they're trying to keep all of it inside, and you're like, it's a public broadcast. Why
did you guys hear this? Yeah. So Vukosi is campaigning to get SABC to release the transcriptions for their stuff. For news.
I think they transcribe like their
radio broadcast. You should speak to Thomas. He's also been trying to get them to do that for 100 years. Yeah. You're not that old, sorry. Yeah, Jeannie.
So a really great data set online that I think like 100 low resource languages that they went and looked for keywords that are unique to low resource languages and found tweets that contain those words, and then create the whole data set that has tweets in different languages.
So Jeannie just mentioned another data set about of low resource of words in low resource languages, and she'll share that link with everyone. You'll try and find it. I'll include it in the slides, and then we'll put the slides online. Okay, so I just want to ask Jay this question, and then I think we'll start to wrap up. Jay, that's your question. What are the most important NLP problems that should be tackled for societies in Africa? And then I'll let you guys ask some last questions.
I think I got the easiest question because I think it's pretty obvious what from an NLP perspective what the problem is, and that's trying to solve for largely low resource problems. But I think in Africa right now, I think what we should be doing is trying to apply a lot of the things that we've learned, just because right now there's nothing, right? So the first thing I would like to look at is education and how it could be used in education, because at the rate that the world is going, there's no way you can translate the resources that are coming in. So if there's a way that we can, from all the way from ground up, from kids level all the way up to papers and things, where people can access whatever they want to know in their own language from an educational perspective, I think that would be amazing, and I think we could start looking there. Yeah, that's what I mostly wanted to talk about. I also think within community building and working between communities, which I think we should be collaborating a lot more, I think that would help there. So then it's low resource language with machine translation. I would say. Anyone else?
Any more questions? You should ask some questions. Comments? Yeah, Stuart.
Yeah. I have a question, but it's related to the first discussion.
Perfect.
Which was had on the panel. It's about whether or not you can actually solve the natural language processing problem without an embodied agent. You guys in the panel, you spoke about this, and you all kind of agree that you would need a simulation environment. You would have an embodied agent. We agree that this is very hard. If like I would say it's probably impossible. So do you think that natural language processing will follow on from robotics, and that's when we're going to solve it, when we can actually embody them in this analog computer in the real world, or not?
Stuart has a very interesting question. So he basically said, going back to natural language understanding, if we basically make the claim that we need embodied agents in order to really get natural language understanding, and at the moment we know it's very difficult to get embodied agents, will natural language understanding essentially have to follow on something like robotics, where we can actually put an agent in an environment? I think that's a cool question.
Yes.
I think everyone has
We'll
some
be
ideas.
here till
Sorry?
Everyone has some
We all have ideas.
thoughts about it.
They have 27 ideas, which they'll also send to me. I'll put them in the slides. Yeah, but Sebastian has the microphone. Go.
Cool. Yeah. So I think we definitely should not wait for robotics, because until we are able to actually have use robots in practice, I think that's going to take a lot longer, and I don't think as a community we have that much patience. So on the other hand, I think those that kind of learning or trying to explore more how we can use like interactivity or simulations for learning language, or what kind of additional information we can get from grounding or incorporating like multimodal information into our models. I think that's like a very, very useful part to do. And then similarly, I think it's really, kind of also aligning like on this problem here. I think it's really that kind of trying to solve like the general AI or like the entire problem of natural language is way too hard anyway. So I think we really need to kind of define or define kind of steps on that way, and really kind of come up with challenging benchmarks really that are kind of slightly out of our reach at the moment, but that can really incentivize people to kind of develop methods that have more capabilities than methods from a few years ago.
There's a cool debate between Jan and Christopher Mann on this topic. He actually touches exactly on that. It's from the AI Salon. I think that's presented.
You'll also send me the link. I'll put it in the slides. Everyone that send me links. Emoji.
Just a reminder.
Yeah, no.
Something I wanted to mention is from the work in cognitive science, one of the things we know is that the way human beings acquire language is also very dependent on emotion. And that emotional aspect, for example, when you think of love, you think of something like warm, cozy. Why do we think love is warm and cozy? You know, and then when somebody breaks up with you, like, that's so cold bastard. Why did he turn cold? It's because it's literally about embodied cognition. As a baby, your mother's womb is warm, and then the bone that holds you, and there's heat transfer, and that actually informs how you reason about relationships. That is going to be very, very hard to put into a synthetic agent. It's not going to have that human element around emotion, which is very central to deep understanding of language. So I just think it's a fool's errand. Nevertheless, we'll do it because good things will come from the quest.
Yes. I just want to mention on that point that the way that we are basically defining the Turing test, it's about mimicry and imitation. And we know that sociopaths have no emotion, and yet they're able to fool people into thinking that they do. So I think that we will be able to find solutions that don't need to be embodied and have emotion, but we'll be able to operate in the real world, understand people have emotions, and be able to help us solve our problems.
Yeah.
Okay, awesome. I'm quickly going to run. It'll take two minutes. You won't miss the amazing food. We actually asked the experts in our email, we asked them a couple more questions, which I'll just highlight some of my favorite highlights. So one of the questions was, what if anything has led the field in the wrong direction? The field of NLP. People spoke about synthetic data, synthetic problems, and I think that's really important. Solving real problems is something that we should be working on. Sebastian Riedel said benchmarking and leaderboard chasing. He said that is the biggest thing that went wrong in the field, and it's actually interesting because again in David Silver's talk just before this, he said that it might actually be a good thing. Okay, so you can go and beat up Sebastian if you don't agree with that. Isabel also said beating the state of the art is something that's really bad. Brink van der Merwe unfortunately couldn't be here. He said Chomskyan theories of linguistics instead of corpus linguistics. That's really something that led the field in the wrong direction, so using Chomsky. Someone else said that not incorporating enough Chomsky into your model has led the field in the wrong direction. Karen Levescu said too much emphasis on Bayesian models. Sorry, smiley face, and she put that there because I did my PhD on Bayesian models. Michael Roth is a good friend. I really like this quote. Ha ha ha, as if the field as a whole moved in a single direction. Which I thought was really cool. Okay, but actually overall, and you can read this quote, actually overall, even the people that had kind of these slightly negative responses, they started their answers more or less by saying, I don't really think there is something like a wrong direction. And both André Sorgaard and, I can't pronounce his name, Miguel, they both kind of said that really it's important for people to kind of explore a broad range of problems, and it's really, really hard to say when things go in the wrong direction. What advice would you give a postgraduate student in NLP starting their project now? I'll leave this, I mean, you can read it quickly. Joshua Benjo, he actually gave some great responses. He said, read a lot, big goals. George Dahl, he really emphasized the power of having very strong baselines, and that's something that I think is extremely important. Ulrich mentioned in the paper writing session that what you should aim to be is you should write that paper with the stupid baseline that everyone tries to beat, right? With the strong but stupid baseline. And I think that's something that's very important, especially for junior students. King Yong Cho, who unfortunately couldn't be here, he also really gave some great answers, basically saying that scientific pursuit is meant to be full of failures. So if you're starting your project, if every idea works out, it's either because you're not ambitious enough, you're subconsciously cheating yourself, or you're a genius. And he says that there aren't that many geniuses in the world, so that's probably wrong. And then Felix Hill, and I think this overlaps with a lot of what Moses said. He had this very interesting comment saying that understand psychology, go to CogSci. Understand machine learning, go to NIPS. Don't worry about ACL, the machine learning, after NLP conferences. Submit something terrible. That was also interesting. He basically made the argument that if you go to conferences, chat to people, get feedback on your work, and that's a very, very valuable way for a PhD student or a master's student to kind of start out their project. Okay, so that was most of the session. What I really want you to do now is, the closing ceremony is now. Get on the buses, eat and chat. One last thing I wanted to mention is I didn't get all the posters at the Indaba, but I read through all of the poster titles which had NLP in them. And what was fascinating to me is if you look at these 4 big open problems, the 4 things we discussed, almost all of the NLP posters could have fit into one of those categories, which I think is just like very inspiring for people working here. Yeah, with that, I'll see you at 7 Sisters.